Hello and welcome to this lecture in the course for Secure Systems Engineering. During this course, we will be studying a lot of vulnerabilities in C and C++ programs. Now, in order to appreciate these vulnerabilities and how attackers have been able to utilize these vulnerabilities to create exploits and malware, it is important for us to be able to understand C and C++ program binaries. So, in this course, we will be restricting ourselves to just C binaries, but a lot of these what we study here can be extended to C++ binaries as well. So, let us start with a small C program. So, as we know, this program over here defines a string called which is initialized to hello world and then invokes the printf function to print that particular string. Now, in order to execute this particular program, the first thing we do is enter this program in a text editor, save it as, let us say, hello.c. Then we use a compiler like this, gcc hello.c, which would create an a.out executable. So, this executable is stored in the disk. So, this executable has a particular format known as the ELF format or Executable Linker Format. So, at a later time when you want to execute this particular program, you run the command /a.out from your shell. When this happens, the operating system gets invoked, it loads the executable file from the hard disk and loads and creates a process out of it which is present on the RAM. The process is then made to execute and you would get the string hello world printed on your terminal. Now, what we would do during this lecture is to understand some details about what this ELF format is all about, and we'll also need to know some details about what this process contains. So, we will start with the ELF format or the Executable Linker Format. ELF format describes a structure by which object files and executables need to be stored. So, there are two views for the ELF format. One is the linker view and the other one is the executable view. The linker view is applicable for object files while executables have the executable view. So, let us start with the linker view. So, an object file for hello.c can be created by this particular command. You do a gcc hello.c, have a -c option, it creates a hello.o. Now, hello.o is an ELF object file. It has a structure as shown over here. At the start, you have an ELF header which describes the entire file organization. Then you have various sections which contain the code, the data, the symbol table, relocation information, and so on. And you also have a section header table. So, in this section header table, essentially there is a structure which would help you locate the various sections present in the ELF object file. There is also a structure known as the program header table, but this is typically not present in the object file. So, we will look at more details about each of these headers, especially the ELF header and the section header. Let's start with the ELF header. So, the ELF header defines a structure with various parameters. So, here we have actually set some of the few parameters present in the ELF header. It starts off with an identifier. So, this identifier is a magic number which can be used to determine whether the file is an ELF file. So, for example, all ELF objects, ELF executables, libraries, and so on would start off with this particular identifier. Then there is an entry in the ELF header which describes the type of this particular file, whether the file is an object, an executable, a shared object, or a core file. So, this information is present in type. Another entry is the machine details. Which processor was this particular file compiled for? It could have entries like i386, x86 64, ARM, MIPS, and so on. What this means, for example, if I have an entry, if the entry is, let us say, ARM, it means that this particular object file or executable was compiled for the ARM processor. Then you have an entry which is known as entry, which describes the virtual address where program has to begin execution. So this is more applicable for executables rather than object files or libraries. So another important component in the ELF header is this pointer to the section header table. So as we said in the previous slide, the section header table is present as part of the ELF image, and it contains pointers to the various sections. Also, there's another entry called the number of section headers present in that particular file. So let us see the ELF header for our program that we have written. So what we do is we say compile the program gcc hello.c, give it the -c option, by which we get the executable hello.o. Then we run this command read elf -h hello.o. The output would look something like this. This output tells you the ELF header information for the file hello.o. Note that it has the magic number, which essentially is the ELF identification. Then it has various other aspects, including the machine details. Here it says that this object file was compiled for AMD x86 64. That is, this object file can be only used by AMD and Intel machines which are configured for 64-bit. Then you have the entry point address, and importantly for us, you have the start of the section headers, which is an offset of 368 bytes into the file. Also, the number of section headers that are present is, in this particular case, is 13. So let us look a little more detail into the section headers. The section header table can be, for this particular program, can be obtained by running read elf with the -s option as shown over here. That is, read elf -s hello.o. The output looks as follows. These are the name. This particular column tells you the name of the various sections present in the hello.o object file. Then you would have the type of the section, and as we see over here, there are various types of the section, starting from programming bits, which essentially contains the program or the code that was written. You could have symbol table, you have no bits, reallocation table, and null, and so on. You have another entry which is known as the address. So this corresponds to the virtual address for the various sections within the object file. So note that since this is hello.o, this is an object file, therefore each of these sections are relocatable. Therefore the addresses present over here are all 0. And then you have two columns, one for the offset and other for the size. The offset specifies the offset within that particular ELF object where you could find this specific section. For example, the .text section, these two columns specify the offset and the size for the various sections present in the object file. For example, the .text section is present at an offset of 34 and has a size of 3C. So 3C here is the hexadecimal notation. So in addition to all of these columns, there are other columns like this. For example, you have a flag column which specifies the various flags for this particular section. So for example, A and X implies that this is A stands for allocated, while X stands for execute, which means that this section contains executable code and can be executed. In a similar way, for example, you have the data section, which is 3 over here, and you notice that 3 has the flag WA. So W stands for write. So note that the data segment is writable but cannot be executed. Now that we have seen the linker view of an ELF format, we would now look at the executable view. So the executable view is applicable for ELF executables. To generate an ELF executable for hello.c, you could run this command like this, or gcc hello.c -o hello. So this creates an ELF executable very similar to the a.out, which is called hello. So the hello executable has a format like this. So note that this format is very similar to the linker view, except that there are few changes. First, you would notice that the sections in the linker view are now called segments. Further, you would note that the program header table is now applicable now, while in the linker view this program header table was not, although it was present, it was not used. While in the executable view, on the other hand, the section header table is not used. So as before, the ELF header describes the file organization of this executable and has the very same structure as what we have seen previously for the linker view. The program header table helps to locate the various file segments, while the various segments present could be used for code and instructions, data, symbol table, relocation information, and so on. So we will look at how the program header table looks like. So the program header table essentially contains various program headers for the various segments. There would be one header corresponding to each segment. So the contents of a program header would look something like this. So it is also defined by a structure and has various entries, and each program header is associated with one program segment. So the contents of the program header is as follows. There is a type entry which tells you the type of that particular segment, whether that segment is a loadable segment, is a shared library, and so on. There is an entry called the offset, which tells you the offset in the ELF file where that segment is present. There is a virtual address entry which tells you where that segment has to be loaded in the process during the execution time, at what location should that segment be loaded in the entire virtual space. There is also a physical address offset which specifies which physical address that segment should be loaded. In most of the cases, this particular entry is ignored, and we have the memory management unit of the processor which takes care of managing the physical address. Besides these, you have the size of this particular segment in the file, and also the size of the segment when it is loaded into memory. And additionally, you have flags for this particular segment which specifies whether that segment can be written to or can be executed. So let us take the hello.c file again, create an executable hello, and then read the program header information. So the program header information for the hello program could be read like this. So read elf with the -l option and then the executable, and you get an output like this way. So note that there are 9 program headers. These are the 1 to 9 headers. It contains an offset into the file where this segment for each of the various segments. It has a virtual address where each of these segments should be loaded when executed. This physical address is also present, but it's not used. It also has the file size and the memory size and the flags present. So for example, you see that there is this section over here which is read and executable. So this is a text section. So this is this particular section has code, and you'll be executing from this particular section. Additionally, an important aspect over here is this particular part that creates a mapping from the section to the segment. So for example, the segment 2 contains all of these sections. Similarly, section 5 has the sections .node.abi tag, .node.gnu.build, and so on. So essentially every section present in the program gets mapped to a particular segment. So now let's go a little more detailed into the contents of the ELF executable. So what we do is we take the hello executable that we have created, and we could actually create the disassembly for that particular executable. So by running the command like obj dump disassemble all hello and saving the output in this file called hello.list, we will be able to get the complete disassembly for the ELF executable. So over here is a small snippet of that hello.list file, and it's only dealing with this particular main program over here. So what we see over here is the assembly level instructions for this main program. So what we see at this particular column is the virtual address, while in these columns are the corresponding instructions. So notice that over here there is a call to printf at PLT. We will see what this actually means in a later class, but for now we can understand that this is the call to the printf which is made over here. Similarly, there are other instructions which are used in this main function. Another important aspect for us is this column over here, which gives you a series of numbers like 59, 89, E5 and so on. What these numbers actually represent are the machine level codes corresponding to each of these functions. So for example, this number 55 implies push %EBP. So in other words, when the processor sees an instruction encoded as 55, it would imply that it has to push this register EBP into the stack. Similarly, if it sees the sequence of numbers 89, EC and 20 present in the instruction, it would imply that the instruction is subtract 20x from the stack pointer. Okay, so now we would move from the ELF executable to processes. So we would see what happens when you run the /a.out on your shell. We would see how the process gets created, and we would see how the ELF executable gets transferred from the disk into your RAM. So when you give the command /a.out in your shell, let us see what happens internally, how your program gets executed. So when the shell receives your command, it would run a function which looks something like this. The function would invoke a fork, which is a system call, and it invokes the operating system. The OS would then create a child process like this. So this particular trail shows your shell, and when the fork system call gets created, a child process gets created. So now you have two processes. In the parent process, the value returned by fork, that is P, has the child's PID, and this is a value which is greater than 0. Now in the child process, P has a value equal to 0. Therefore, the parent process would execute this part of the code, while the child process would execute this part which is present in green. Now in the child part of the code, there is a second system call that gets invoked, which is the exec system call, where the executable hello is specified. So this is the hello world program that you need to execute. And at the same time, the parent process invokes the wait system call so as to wait until this child process completes its execution. So let us look a little more in detail about the exec system call when it is executed by the operating system. So when the exec system call is invoked in the operating system, the OS would create a new virtual address space for the new process. It would then load segments from the executable file stored in the hard disk and copy them into the virtual address space. For example, all the segments comprising of the instructions and code are copied into this text segment. All the data, the global data and the static data are copied into this data segment. Now we've taken here a small program. So this particular program computes the factorial of an integer n by this function fact, which is essentially a recursive function. When this program is compiled, an ELF executable gets created, and when this program gets run, the virtual address space for this program gets created by the operating system. The OS would load the code segments of this particular program into this text segment. It would load the global data such as calls into the data segment, and whenever there's a malloc like this, which is dynamically allocated data, so this data gets allocated into the heap. So finally we have the stack segment, which comprises of the local variables. So in the function main, the local variables are n and m. So these local variables are present in the stack. So besides these, the stack also contains various aspects for function invocation and parameter passing from one function to another. So details about this virtual address space can be obtained from the proc directory present in your Linux operating systems. On a Linux system, we would be able to look at the virtual address space while the hello world program is executing. So this is done as follows. First, we need to get the PID of the hello world program. So for that, we could run ps-ae and grep hello. So we get a line like this, where we see that the process hello is present and it has a PID 6757. Now the file /proc 6757/maps contains the virtual address space for this PID 6757, which corresponds to our hello executable. So the virtual address map looks something like this way. So as you can see that there are various segments that are present, some which are present in the hello program itself, some which are present in the libc library, while the other are present in the loader library. Also present is the stack and some internal segments like the VDSO. Now this particular column present here specifies the various virtual address ranges for the various segments. So for example, we have in the hello executable, we have a segment which starts at 080490000 to 08048A000. The second column specifies the various flags for each segment. So for example, this particular segment which is present in hello has the is readable, writable and executable, while this segment cannot be written to, it is only read and write flags are set. Now these three columns specify details about from where the segment was actually loaded from. So for example, this column specifies the offset in the ELF file from where the particular segment was loaded. Now this particular column specifies the hard disk number or the device number, this is the major and the minor number for that particular disk, from where this particular library was loaded. And this last column over here specifies the inode number, which is essentially an identifier in the disk for this particular library. So we have all of these information completely specifying the virtual address map for a particular process. So one thing to note is that for the stack segment, we see that the offset in the file, device number and the inode is 0. So this is because the stack segment is created dynamically and at runtime, and the ELF executable and the ELF object files do not have any notion about the stack. Now we will look a little more in detail about how the stack is managed in the program. So now we will see how the stack of a program is managed during the execution of the program. So we will take as an example this particular program, which comprises of two functions, a main function and a fact function. The objective of this particular program is to determine the factorial of this number n, which is specified by the user. And the way this factorial is computed is by the function fact, which is a recursive function that gets invoked until a becomes 1. So note that fact takes two parameters, one is int a and another one is a pointer, and the other one is an int *v. To understand how the stack is managed, we would have to know about two registers. One is the stack pointer register, which is denoted as ESP, and the other one is the frame pointer register, which is denoted EBP. Now we represent the stack by this particular diagram. So we have the frame pointer pointing to a location in the stack, and we have a stack pointer pointing lower down in the stack. Every time we push something onto the stack pointer address reduces as we keep pushing into the stack, while as we pop from the stack, the stack pointer address keeps incrementing again. So we further define something known as an active frame, which comprises of the region between the base pointer to the stack pointer. When the main function gets executed, and let us assume that the program counter is pointing to this particular location. Now when the main function is executing and the program counter is pointing to this particular instruction, then we have this thing as the active frame. So we call this as the main stack frame, and it is the active frame because it is between the base pointer and the stack pointer. So this region is the active frame. Now in this region we have all the locals that are present in main to be present over here. That is, the locals n and m are mapped to regions, to memory regions present in this area. Now let us see what happens when the function fact gets invoked. So the first thing that main would do is to push the parameters n and m onto the stack, and then it would call the fact function. The call instruction would automatically push the return address onto the stack. So the return address would be the instruction just following the fact function, and it would indicate the instruction to be executed soon after fact returns. So therefore, after the call to the fact function, you would have a frame, an active frame which looks like this. There are the main the locals of the main function, that is comprising of n and m. You would have the parameters to the fact function, which here again would be a copy of n and m, and then you would have the return address. The next thing what happens is that the fact function starts to execute. So the first thing that the fact does is to copy the frame pointer, which was previously pointing to this location. So this frame pointer gets copied onto the stack, and then the frame pointer is moved to this location. So now what we have seen is that we have got a new frame, and this is now the active frame, and it is, we call it as the stack frame for the fact function. The locals for the fact function are then present on the stack, and these locals are present between the base pointer and the stack pointer. So as the fact function executes, it will recursively invoke the fact function. So in a very similar way as we have seen before, when the fact function gets invoked again, parameters to the fact, return address and the previous EP gets pushed onto the stack, and similarly there is space present for this fact locals. So on the first return from the stack, the previous base pointer, which is pointing to the previous frame, gets loaded into the base pointer, and therefore we would get the new fact frame. With this we have given a small introduction to ELF, loader and executable formats, and then we've also seen how processes execute and load these ELF executables and create virtual address spaces, and finally we have seen how the stack in the program operates. So one thing for you to think about is about the command line arguments. So as we know, the main function actually takes two parameters. One is an argc and an argv. So one thing that you could think about is how are these arguments actually passed from the command line, that is from your shell, to your program. Thank you.